I just started the recording. So.
Okay. All right. Thank you very much, you guys, for having me speak here. Today I'll talk about getting high on grouping Orbifolds, and this is based on some work with Miriam Svedich, Max Hubner, and Jonathan Heckman. Okay, so the main idea of this talk is, well, first of all, the setting in which I'll be discussing is non-compact Calabi-Yau threefold singularities with an M-theory compactification. So in particular, I'm interested in engineering 5D superconformal field theories. In particular, 5D superconformal field theories built from non-isolated singularities. Namely, there are 80 E singularities that may intersect at some origin, and I want to today discuss some claims on the strongly coupled fixed point. So in this case, this theory Tx would have a flavor symmetry being the sum of the flavor symmetry being a Lie, having a Lie algebra, which is the sum of SU5, SU10, SU15. The main claim is that there's a general procedure to extract the global structure of this flavor symmetry group, namely its center, as well as a two-group structure of this theory. So namely, that's an interplay between the global structure of this flavor group G and one form symmetry group. So this talk will mainly restrict to these 5D cases, but these ideas apply much more generally. So for example, in the paper, we discussed several examples with G2 manifolds engineering 40 n is equal to 1 theories with two-group structure. This refines some earlier results in the literature which calculate the one-form symmetry as this group here. By this, I mean I'm assuming electric polarization throughout. So I won't necessarily go into what that means if you're not aware, but essentially I'm taking a certain polarization of a defect group so that my so-called electric one-form symmetry will look like this. And I write punch, drag, and dual here because these technically this H1 boundary of X, where X is some non-compact Calabi-Yau threefold. This gives the charged operators of the theory, and then the symmetry group is the punch, drag, and dual of your group of charged operators. And the main takeaway is essentially a geometric characterization of a exact sequence which characterize the two-group structure of the theory. So basically, I'll fill out other entries of this exact sequence with geometric definitions analogous to this one right here for the one-form symmetry. Notation-wise, this ZG is meant to be the center of the flavor group. And so namely a prediction of this thing, even when the one-form symmetry is trivial, will state what the center of the flavor group is and hence give the global structure. And I should also mention there are some related results from a paper published on the same day as ours by these authors. So the plan is first I'll review some generalized global symmetries, namely sort of modern ways we think about zero form and one form symmetries. And then I'll give a rough geometric derivation of these of how to derive these symmetries in the M-theory context on non-compact manifolds. And then I'll explain some examples in the case where this non-compact Calabi-Yau threefold takes form C3 mod gamma, where gamma is some discrete subgroup of SU3. And then I'll end with some conclusions. So just to review some zero form symmetry. So this is just the symmetry taught in every QFT textbook. And for now, I'll just denote this ZG. So it'll just be a center of some flavor group, let's say. In the continuous case, this can always be nicely written as the conservation of as the conservation of some conserved current. So namely, d star j is equal to 0. And given this relation, you can build an operator as so. So in the case where this zg is equal to u1, I can just insert some sort of phase alpha here. And then this property will tell me that this operator is topological. And so if I have some sort of local operator, which is charge k under this U1, and I act by this codimension 1 guy in, let's say, 40, because I made this thing a 3 manifold, then if I collapse this operator on top of the local operator here, then I'll end up with this local operator, which is a phase times my original one, according to the charge. And I can generalize this story to line operators, which is, and the symmetry for these guys is known as one-form symmetry. So in the example where my one-form symmetry is a Zn, then I have a certain equivalence classes of line operators labeled by the Pontryagin dual Zn, and which are namely the representations of Zn. So given a representation of Zn with the label k, then this line operator here will transform according to this phase. And I mentioned this equivalence relation here. The equivalence relation looks like as follows. Two line operators have the same one-form symmetry charge if they're separated by a local operator. I'm calling a cal p. So line operator here, line operator here, and this implies that under this tilde that I'll just write them as having the same one-form symmetry charge. And there's another equivalence relation I'll mention, which I call naive one-form symmetry. So I first learned about this in this paper right here, and we'll define a coarser equivalence relation, which then means that we have a larger group. So I'll restrict to the case where I call cal OL is equivalent to some cal OL prime if you can separate them or bisect them, I guess, with a genuine local operator, which I'll define in a second. And given this sort of coarser equivalence relation, tilde prime, I can define my one-form symmetry group as being line operators modulo this coarser equivalence relation. So to explain what I mean by genuine local operator, because before I was just talking about all local operators, by that I mean, or one way to define it is it's faithfully acted upon by the zero-form symmetry. In other words, they form representations of the zero-form symmetry group, not projective representations. This also is equivalent to saying that any non-genuine guy is ended by some sort of topological line operator, or it's secretly a cut. So if you were to calculate, if you were to calculate correlation functions involving these guys, you would have cuts in your space-time variables. So a emblematic example of this would be the twist operator in an Ising CFT, for example. So those can only be defined as being the endpoints of some topological line operators. Given this data, we could say that these non-genuine local operators transform projectively under some group ZG, which equivalently means that they transform faithfully, i.e. non-projectively, under some finite cover of ZG. So this finite cover we'll call the naive flavor symmetry group. Okay. So given this finite cover, which I just mentioned, I can consider the kernel of this thing and then present this as a short exact sequence. And furthermore, I have another short exact sequence coming from these equivalence classes of line operators I mentioned. So the equivalence classes of line operators with respect to delta prime forms this cal A tilde, and it extends the normal class of equivalent class of line operators up to that measures their one-form symmetry charge. And it turns out that the C is that these this C check is the Pontryagin dual of the C here. Now, if I take the Pontryagin dual of this sequence, which reverses all the arrows, I can collapse the two sequences and then get this 4-term exact sequence, which is sort of measured by this group cohomology class. So similar to how short exact sequences, their non-splitness, so to speak, is measured by a second group cohomology class. 4-term short exact sequence, or sorry, 4-term exact sequence is measured by a third cohomology class, which throughout this talk we'll just refer to as the Plotnikov class. Okay, so what is a true group? I'll just be sort of brief on this. So abstract nonsense definition is that it's a two-groupoid with one element. But in practice, sort of unpacking this, we have this tuple here where pi1 could be a generally non-abelian group, pi2 is an abelian group, rho is some action of pi1 on pi2, and then finally this Plotnikov class that I mentioned on the previous page. Now for our examples, rho will be trivial. So this local cohomology, or sort of local coefficients right here, will end up just being global coefficients, which simplifies things a bit. And for us in a two group, pi1 will be the flavor symmetry, or also really focusing on the center of this flavor symmetry, and pi2 will be the one form symmetry. These are some nice papers to see some more details on this. So now let's see how to see these ingredients from the geometry. So generally speaking, our boundary geometry partial X will be of this rough form. So we have several ADE singularities of various types. These are finite subgroups of SU2, and we'll be interested in M2 branes wrapped on 1 cycles in partial X times a radial direction. So that's what I mean by cone here. So they extend along a radial direction in proper X, and additionally a space-time direction. In other words, these things will become elements in, I can think of them as elements in the one form symmetry group, or the Pontryagin dual one symmetry group. Yeah, so just to summarize where the M2s are living, it's a 1 cycle in the 5D space-time, which is why I'm considering it to be a line operator in the field theory. It's a 1 cycle in partial X, and it fills a radial direction in X. That is this is sort of an old story right here. But now we'd like to look at the refinement, namely how to reproduce this A tilde check, those line operators. And so namely, we would want to look at how to build operators in the C check. And then we'd have all the information we could discuss for this guy. So to do that, first, let's note that from a field theory perspective, the line operators in this C check are line operators which are trivial under tilde, but not under tilde prime. Or equivalently, there's line operators which can end on non-genuine local operators. So to try to cook up what these would look like from the geometry, we'd first consider that if we zoom in on a single singularity here, and wrap the M2 brane on this 1 cycle here, that would lead to a line operator in spacetime, which is a representation of the of basically of abelianization of lambda. So basically, just jump ahead slightly. Basically, if I have an an minus 1 singularity here, then the boundary of this space will include an S3 mod Zn lens space. And if I wrap this gamma along any element of the homology group characterizing this, of the torsional elements for characterizing this lens space, then I can associate gamma as an element in Zn, which alternatively can be seen as a representation of the center of SUN. So what was I going to say? So to back up slightly, if I fill in this disk, so to speak, so now I'm considering a 2-cycle that hits the singularity, and wrap an M2 on this disk, then I get a line operator in the space-time, which ends on a local operator. So this guy will be associated to the boundary here, and then this local operator will be associated to the interior part of this disk. And so basically, this what I want to say is that I can end this local operator because this local neighborhood is topologically trivial. I can end it with a local operator that faithfully transforms under Zn for the A type case. This is like an ultra local perspective. So this is agnostic as to whether this line operator ends up being in C or ends up being a trivial element in C. Because if I try to complete the space and I have a single ADE singularity, then it may be that this line operator is actually trivial in the homology. Like I can contract it all the way around. So in that case, that would be a trivial element in C because I can then wrap an M2 brane on a disk that's in the complement of this disk. In other words, if I look at the space-time, then this local operator would not be a representation of this Vn, and that means it would just be a trivial element in here. So this sort of motivates the geometric characterization that MathCal check is torsion H1 of partial X with the singularities removed. So with this definition, then C check would be torsion of the kernel of this map. So I embed a partial X circ, removing these singularities. And then and then the kernel of that map would correspond to elements in C. So if we can also motivate the fact that if we look at basically the boundaries of local neighborhoods around the ADE singularities, then this homology group here would be the sum of the abyelianizations of lambda. So basically, the chalkboard I could explain a little better, but basically, the non-trivial torsion piece here ends up being, you can collapse it to H1 of S3 mod lambda for each sort of set of ADE singularities. And then this naive flavor symmetry will be the sum of all these things. So putting all these pieces together, you can end up seeing how these all can be placed in terms of inside a Meyer-Beer torus sequence. So if I let's see, so Meyer-Beer torus sequence is a long exact sequence, and then from long exact sequences I can extract short exact sequences by taking a given element and then giving a short exact sequence where I extend by the kernel in the image. And if I take two such short exact sequences, I can create an exact sequence with 4 terms. And this exactly reproduces, given the definitions on this slide, this long exact sequence that is motivated by the field theory to characterize the 2 group. Let's see. And this basically ends up giving the machine that we can then apply to several 5D theories as well as 4D theories. So I'll just briefly mention that you can also characterize these pieces in terms of orbifold homology, or I'll just briefly mention that if for a boundary space, so X is a little more abstract in this slide. So for boundary space X, if I cut out the orbifold singularities, H1 of this thing cut out is equal to the orbifold homology of X. So I can just briefly motivate that by saying that this gamma here that wraps a torsional cycle in this S3 mod Zn is part of the twisted sector of the orbifold quotient characterizing this AN-1 singularity. Okay. All right. So just to mention some examples. So in the case where our Calabi-Yau threefold is C3 mod gamma, this constructs a 5D N-1 FCFT at the origin. And typically this is studied by resolving or deforming the singularity. And what's very useful in these sort of global orbifold cases is that you can use a 3D Mackay correspondence and nicely see how a lot of group theoretic data of gamma gives you physics information. For example, the ranks of the gauge and flavor groups nicely fall out by quick definitions from gamma. And so we'll focus on the case where gamma is abelian. Then there's 2 possibilities, it being Zn or Zn times Zn, or M divides N. Then in the case where, in the first case, then the action is given as, the general action be given as follows, where the sum of these weights is equal to 1 because it's a subgroup in SU3. And we can have anywhere from 0 to 3 flavor branes parametrized by the arguments of Zi. And these flavor branes necessarily hit the boundary along a circle quotient. Another possibility, and then for the case of Zn times Zm, we have an additional generator by this nth root of unity. So generally speaking, the toric geometry of this space will sort of look like a cone over a triangle. In other words, it'll look like an octant in the positive octant in R3. And then the boundary of that space naturally looks like a filled-in triangle. So this will be the toric base of my S5 mod gamma. So in general, so the fiber will be T3 mod gamma, which means it'll be 3-dimensional in here, 2-dimensional as I hit the edges, and then 1-dimensional circle for each of the dots. And these can be, in general, some A-type singularities localized along these circles. So to consider the Tn theory, so it's given by the following action. And in that case, all of 3 singularities are AN-1 singularities. Then in that case, using the relation orbifold homology, I can quickly see that the naive one-form symmetry is Zn squared, because the orbifold homology of some simply connected space modded out by something, in this case modded out by Zn times Zn, will always just give me the group that I orbifolded with, so Zn squared. Also, using Armstrong's theorem, which states roughly that the the fundamental group of the quotient by this Zn squared is the subgroup which acts non-freely. So in this case, all of the generators here leave some fixed points. So therefore, the fundamental group in the first homology group is trivial. So from there, using these short exact sequences, we can then state that C is equal to Zn squared, and then using this factor here.
Sorry to interrupt. Just so you know, you have 5 minutes left, including questions. Okay.
Okay, sure. So I'll just finish up with this example and then flash some stuff. Okay, thanks. Then using this information here, I can then this implies that ZG is equal to Zn. So I should say that the ZG tilde is equal to Zn cubed, which is also needed for this because I have 3 an minus 1 singularities, and my naive flavor symmetry is just the sum of 3 Zns. So therefore, I can state that the global flavor group is going to be SUN cubed mod Zn squared. And then up to some subtleties with symmetry enhancement for the n is equal to 3 case, which is not yet available to this procedure. But for n not equal to 3, this gives the correct answer. And even for n is equal to 3, where we expect a E6 mod Z3, this gives the correct answer when you consider the embedding of SU3 cubed mod Z3 squared. And I'll just flash an example with a non-trivial 2 group. Running through the machine again, then in that case, we can state what the global structure of the flavor group is, and also have a non-trivial one-form symmetry, in this case Z3, whereas the one-form symmetry in the Tn case is trivial. So just to summarize, introduced a general procedure to calculate the 0-form, 1-form, 2-group symmetries. 0-form and 1-form are novel, except I should mention that the 2-group structure for global quotients, namely where the Calabi-Yau threefold is a global quotient, was conjectured in this paper. This can be applied to many other examples. So for example, see our paper for some more details. And so one sort of nice generalization would be nice to see some sort of symmetry enhancement, and also apply to compact models. And of course, this fits into a general paradigm, that's a hot topic right now of categorical symmetries. And it would be interesting to sort of see how those pop up in an analogous geometric procedure as well. Yeah, that's.
Okay, thank you very much. So, are there questions? Okay. People are clapping. Okay, Iñaki has a question. Yes, please go ahead.
Hello, thanks for the nice talk. I had a question. At some point, you referred to genuine operators, and you define them as those that transform under faithful representations of the symmetry group.
Yeah.
But in the context that you use them for equivalence relations, they were the ones that were connecting lines, right? Well, another definition is that you have the operator not attached to any line. So can you comment on the relations of those two definitions, if there is any?
Yeah, so a genuine local operator can can sort of bisect two line operators or be the end of a line operator, but a non-genuine local operator must be the end of a topological line operator. So that's,
I have no problem with the
the key.
definition of non-genuine. My question was for the definition of genuine. So typically we'll use genuine to say something that's not attached to lines.
Yeah. So genuine does not have to be attached to a line. But
so in concrete terms, in your previous slide, can you go back one slide?
Yeah, sure. Right.
Can I take that operator there out of the line?
Let's see. So not out of Yeah, so equivalently, if you let's say you fold this diagram, let me think about this. So what I'm thinking of is if you have like n is equal to 4 superioring nils, you can end a Wilson line operator in the adjoint on a let's say like a glue ball operator. Then in that case, let's see. Yeah, in that case, you can't remove the local operator because it's changing your line operator as you go from here to here. But the point is that you could define it as not bisecting two line operators. Another thing you could do is you could take more genuine local operators and then put them on this guy and then remove the local operator that started there. So going back to the 40 n is equal to 4 case, you need some sort of local operator that transforms. Let's see. Yeah, let's say you need some sort of local operator that transforms into the adjoint of the gauge group in order for the configuration to be gauge invariant, so to speak. But yeah. So yeah, so they can bisect line operators, but they can be defined without operators. Yeah.
Okay, thank you.
Okay, any other question? Very quick. We have to change to the second talk. Okay, in that case, let's thank Ethan again for a nice